We're getting started with Unit 7 today, so we're going to go through, in this video, we're going to go through 7.1 all the way through 7.6, and what we're talking about in Unit 7 is something called equilibrium. So let's get started. Unit 7 is all about equilibrium reactions, and so what I want you guys to notice is in this equation right here, all the reactions that we've dealt with so far in chemistry have all been reactions that have had just the forward arrow only, and we have our reactants on the left, and we have our products on the right, and the reaction proceeds and produces our products. With equilibrium, what we have are reactions that are happening in a closed system, which means basically nothing is allowed to escape. And when you have reactions take place in a closed system, sometimes those reactions are reversible. So when we talk about equilibrium, we're talking about reactions that can not only go forward, but also reactions that can go backwards. And what happens is with equilibrium, so let's say that when I start this reaction, I take A and B and I put them in a container and they start to react. Now, over time, that reaction is going to start to slow down because my concentration of A and B are going to decrease over time. So that rate of reaction decreases. And as I produce C, my product, as I get more C, that C will start to turn around and decompose and turn back into A and B. So the rate of the reverse reaction, initially there is no reverse reaction because there is no C. Once you have enough C, it starts to go backwards. So the forward rate decreases, the reverse rate increases, and when those rates are equal, that's when you have equilibrium. It's not about the amount or the concentrations of the things that are in the container, it's about how fast those forward and reverse reactions are taking place. So if we look at this graph down here, the amount, this would represent our concentration in molarity. Our product amount is going to increase over time. Our reactant amount is going to decrease over time. And eventually, those concentrations don't change anymore. That's what you have at equilibrium. They're not the same as each other, but they're constant. So it's important for you guys to know that the concentrations of all components stay the same at equilibrium, but the reactions continue to happen. You still have forward reaction happening, you still have reverse reaction happening, but they've reached equilibrium. All right, as we deal with equilibrium reactions, we're going to deal with something called the equilibrium constant, which is K. So that's what we're going to talk about. The equilibrium constant it's just a ratio. So it's a ratio of how many products to reactants you have at equilibrium. And what we're going to do is we're going to take our products, and those are going to go on the top of our equilibrium expression, and our reactants are going to go on the bottom of our equilibrium expression. So if we take a look at this equation, I've got A, B, C, and D as my capital letters. Those are my reactants and products. So you can see that C and D are on the top of my expression here. A and B are on the bottom, products over reactants. Also, coefficients become important when we talk about equilibrium expressions. Those coefficients become exponents in our equilibrium expression. So we're going to write some examples here in just a minute. They'll show this as K equilibrium, the equilibrium constant. Sometimes they'll show it with a C also to represent the equilibrium constant based on concentration. So you might also be asked to write KP expressions. KP expressions are done exactly the same way, except for instead of brackets, remember brackets equal molarity. So instead of brackets, we're going to be dealing with pressures. P represents pressure. So I would say the pressure of C to that exponent, whatever the coefficient is, times the pressure of D. So it's set up exactly the same way, but it does look a little bit different to specify that we're dealing with pressures instead of concentration values. All right, things that you guys need to know about K. You need to know what it means if K is greater than 1, less than 1, or equal to 1. So if K is greater than 1, it means that there are more products at equilibrium. Sometimes they'll say that the products are favored So you'll see that terminology. The products are favored if K is greater than 1. If K is less than 1, there's more reactants, or the reactants are favored. And if they're equal to each other, then you basically have the same amount of products and reactants at equilibrium. Let's go ahead and take a look at this example. So we're given the overall reaction, and then we're asked to write the K expression. So the K expression is going to be equal to my products over reactants. This should say that this is a gas, SO3. So I'm going to have products is SO3 in brackets there. That's going to be squared because the coefficient is 2. And then on the bottom I have my reactant. So I have SO2. That also gets squared because the coefficient, and then oxygen, which has no coefficient, will have no exponent. That's my K expression, is just writing products over reactants with the correct exponents. And then it actually asks us to calculate K, so we can go ahead and plug in the numbers that they give us for concentration. You do have to be careful. In this particular example, they give us all molarities, so I can just plug them in. If they give you moles and liters, then you have to calculate the molarity first. So let's plug in our SO3 is 3.5. That gets squared. SO2 is 1.5. That gets squared. And then O2 is 1.25. So I can go ahead and calculate K. When you plug that in, you should get 4.36. Some important things for you guys to know about K. K has no units. It's basically a ratio of products to reactants, so that's all I need here. This is basically telling me that since K is products over reactants, that means the products are favored at equilibrium, or you have more products than you do reactants when K is greater than 1. Okay, but no units there for K. Also important to know, solids and liquids are not included in equilibrium expressions. We're only going to include gases or aqueous substances only. So what that means here for the second example, calcium carbonate is a solid, calcium oxide is a solid. So if I'm going to write the K expression, I should put a C up there too. I'm just going to do products over reactants. That's just going to leave me with the concentration of CO2 because everything else is not included in my expression. Okay, we're also going to be calculating something called the reaction quotient, which is capital Q. We calculate it the same way that we calculate K. So if we look at this example, calculating Q is going to be products over reactants. So I'm going to have HOCl, that's going to be squared. I'm going to have H2O on the bottom, and I'm going to have Cl2O. We use our expression the exact same way that we calculate K. The only difference is the values that they give us are not at equilibrium. So all these pressures, oh, these are pressures. I should have put this as pressure instead of concentration. That's okay. These values are not at equilibrium. These are just values that are given. What you have to do is to figure out if a system is at equilibrium or not. So there are some guidelines right here to help us figure that out. Let's go ahead and plug these numbers in and see what we end up with. So HOCl has a pressure of 21 torr. That's squared. H2O has a pressure of 200, and then Cl2O has a pressure of 49.8. That's going to give me a value of 0.044. What I want to do here is I want to compare this number to my K value, and I want to compare to see which one is bigger. So in this particular case, Q is less than K. So a lot of people try and memorize this right here. If you try and actually just reason through the thinking, you can figure out what has to happen in order for equilibrium to happen. So if Q is less than K, that means that the number on the bottom, there's too many of those. And since the number on the bottom is too big, that's why my Q value is smaller than K. So I have too many reactants. And if I have too many reactants, then the reaction is going to want to get rid of those extra reactants. And so what we're going to say is that that forward reaction is going to be favored or speed up to get rid of the fact that there are too many reactants. And then when that forward reaction happens, it can regain equilibrium. So we want to calculate Q the same way we calculate K. We want to compare the two values, see which one is bigger, which one is smaller, determine if we have too many products, too many reactants, and then whichever reaction will get rid of the extra stuff, that's the reaction that's going to be favored. K values can be really small. So as we go through the next couple units, we'll deal with K values that have anywhere times 10 to the negative like 70th even, and then it'll range all the way to numbers that are really big, times 10 to the 70th. I mean, that's not necessarily exactly the range, but the idea is that you can have really big numbers for K, you can have really tiny numbers for K, and that's okay. But you do need to know what that means. Large K values, like these ones over here, represent reactions that basically go to completion. All the reactants turn into products. And if you have very small K values, that forward reaction barely happens at all. You have a very small amount of product formed. So sometimes you guys will be given a reversible reaction, and they'll give you the K value for that reaction, and then they'll ask you to find K for reactions that are similar but slightly different, like they might be reversed reactions, or the coefficients might be multiplied by a number, or you might be adding reactions together. So we have to know how to calculate the new K value based on the reaction and the K value that we're given. So let's look at a few examples. All right, so we have this example where I've got nitrogen and hydrogen reacting to form ammonia. So when I calculate my K value, or when I write my K expression, it's going to be products, so that's NH3 squared over reactants, so N2, and then H2 cubed, and they give me my K value. My K value is 4.0 times 10 to the fourth. So then we have these other reactions that are given to us, and it asks us to solve for K for all of these different examples. So we have to notice all three of these examples are similar to this, our original equation, but they're just slightly different. So if we look at number one is the reverse reaction. So it's just flipped. NH3 becomes my reactant, nitrogen and hydrogen are my products. Whenever you reverse the reaction to solve for the new K value, you're going to take 1 over the original K value, which is 4 times 10 to the fourth. So my new K value is going to be 1 over 4 times 10 to the fourth, and that's going to give me 2.5 times 10 to the negative fifth. So again, anytime you flip the equation, we inverse our K value, because basically what we're doing is we're just changing which ones are the products and the reactants. Take a look at example number 2. Example number 2 has the reaction in the same direction, but the coefficients are multiplied by 1/2. Whenever the coefficients are multiplied by a certain number, we're going to take our original K value and we raise it to that power. So K to the 1/2 power is going to be my new K value. It's basically the square root, and that gives me 200. When I look at example number 3, again, my coefficients are multiplied by 3. The reaction is in the same order. Sometimes you will have to reverse the reaction and multiply it, so you'll have to do 2 different things to the K value. In this case, my coefficient is just multiplied by 3, so I take my original K value and I cube it, which gives me 6.4 times 10 to the 13. The last thing that I want to talk about in this section, this is the last part of 7.6, is kind of goes along with what we did with Hess's law, which is if you add reactions together to get an overall reaction, what do you do with those K values? So you might get an overall reaction like the one that's given here, and then they'll give you separate steps, step 1 and step 2, and they'll give you the K values for each one of those 2 steps. And basically what they're going to ask you is to figure out what the overall K value is based on the K values of the original steps. Now, in this one, HCO3 cancels. When I add those reactions together, I don't have to do anything. I can just keep this one, I can keep this one, and just add them together. Whenever you add reactions together, your overall K value, you're not going to add the K values together, but you're going to multiply those K values together. So with delta H's, we added all the delta H values with our K values. Once we add our equations together, we just multiply those K values. Let's take a look at another example. Okay, in this example, we're given our K values for our first 2 equations, and we're asked to find the K value for our third equation. Even though they don't show it this way, you should be able to combine the 2 reactions that they give you the information for to equal your third reaction. So if we take a look at this, I'm going to have to multiply my second equation by 2. That's going to give me 2F minus, which will cancel with that 2F minus. It'll give me 2 hydrogens. It'll give me 2 HFs. So when I want to solve for K3, not only do I have to multiply K1 and K2 together, I also have to take K2, and since my coefficients had to be multiplied by 2, remember when we multiply our coefficients by a number, we raise our K value to that exponent. So K2 has to be squared and then multiplied by K1 to get K3 for my overall reaction. All right, that is it for our notes for 7.1 through 7.6. So we're going to do a bunch of practice with this in class, so I will see you guys then.